You know those ball and stick models of molecules we all saw in high school? They're simple, they're clean, and they're not really the whole story. Today, we're going to peel back that simple picture and uncover the beautiful and honestly kind of bizarre, true shapes of chemistry. We're going to see how everything from a vibrating guitar string to the wild rules of quantum mechanics dictates how our entire world is built. So here's where we're headed. First, we'll see exactly why those old models just don't cut it. Then, we're diving deep into the strange world of quantum mechanics to meet the electron as a wave. From there, we'll see how that one single idea gives atoms their real 3D shape. Then, we'll use those shapes to actually build chemical bonds. And finally, we'll put it all together and see how this powerful new theory just perfectly explains the world around us. Let's get into it.
All right, so let's start with what we all know, those simple stick figures from chemistry class. They're a great starting point for sure, but as we're about to see, they're hiding a reality that's so much more interesting and way more accurate.
And this, right here, is the central puzzle. If a chemical bond is really just a straight line, then why is a water molecule always bent in that specific V-shape? Why is methane always a perfect little pyramid, a tetrahedron? The lines themselves, they don't tell us. They can't explain the why behind a molecule's specific functional shape.
And look, this isn't just a minor thing. The simple Lewis theory flat out fails for a lot of compounds. It can't predict their structure or their chemistry. It's clear we need a better model, one that's based not on, convenient drawings, but on the fundamental physics of how an atom actually works. So, where do we find this better model? Well, this is where things get a little weird, but it's also where the whole solution is hiding. We need to look at the secret life of the electron. And the key, the absolute game changer, is to stop thinking of it as a tiny little ball and start thinking of it as something much, much stranger, a wave. It all comes down to this wild idea from quantum mechanics called wave-particle duality. Back in the 1920s, a physicist named Louis de Broglie suggested that tiny particles like electrons don't just act like little points zipping around. They also behave like waves, kind of spread out in space. And that one idea, it changed everything. To get our heads around this, let's think about something familiar, like a guitar string, right? You pluck it, it vibrates in what's called a standing wave. It can have simple vibrations or more complex ones, harmonics, but here's the key thing. It always has these points called nodes where there's zero movement at all. An electron's wave, trapped inside an atom, behaves in a very similar way. Now, let's level up. In 2 dimensions, that wave is less like a string and more like the head of a drum. When you hit it, it vibrates, and you don't just get points of no motion, you get entire lines or circles where there's no vibration. The patterns start to get way more intricate and structured. So this leads to the big question, right? What happens when we take this idea of a standing wave and expand it into the 3-dimensional space that an actual atom lives in? The answer to that, well, that's where all of chemistry gets its shape. So what happens in 3D? Well, that electron wave isn't a string or a drumhead anymore. It's more like a cloud, a fuzzy region of probability that's described by a mathematical function. And we call these beautiful, functional shapes atomic orbitals. Suddenly, the shape of molecules isn't arbitrary at all. It's a direct consequence of these waves. So let's be super clear here. An orbital is not a path. It's not like a planet orbiting the sun. It's way more like a weather map or a heat map, showing where the electron is most likely to be at any given moment. These maps are the solutions to Erwin Schrödinger's famous wave equation, and they are the fundamental building blocks of an atom. So check out the basic shapes. The simplest orbital, called an s orbital, is just a sphere of probability. Simple enough. But the next level up, the p orbitals, they have this really cool dumbbell shape. And just like the drumhead had a line of no vibration, these have a whole plane of zero probability, a nodal plane slicing right through the middle. The electron is never, ever found there. Okay, so cool shapes, but why should you care about these abstract clouds? Because their shape, their geometry, it's everything. These orbitals are basically the hands that an atom uses to connect with other atoms. Their specific shape dictates exactly how and where chemical bonds can form. So how do these orbital hands actually connect? That brings us to how atoms hold hands. A chemical bond isn't a stick. It's the direct physical overlap of these electron probability clouds. So just picture this. You've got 2 hydrogen atoms floating around, each one with its own spherical s orbital. As they get closer and closer, their electron waves start to interfere with each other, just like ripples in a pond. This interference, this overlap, That is the chemical bond. Now, when any waves overlap, two things can happen. If their peaks line up, we call that in-phase overlap. They add up and reinforce each other. In atoms, this creates a stable, low-energy bonding orbital that really holds the atoms together. But if a peak from one wave lines up with a trough from another, out of phase, they cancel each other out. And that creates an unstable, high-energy antibonding orbital that actually pushes the atoms apart.
So here's the result. Those two original atomic orbitals combine to form two brand new molecular orbitals. Now, nature's kinda lazy, so the electrons will always fall into the lowest energy state they can find, which is that stable bonding orbital, which we're calling sigma here. And just like that, you formed an H2 molecule.
All right, last section. Let's bring this all home and connect it back to the real world. Let's see how this powerful new theory actually works and how it solves the problems that the old stick figure model couldn't even touch. Okay, here's that classic puzzle. A carbon atom has 3 of those dumbbell-shaped p orbitals, and they're all oriented at 90 degrees to each other along the x, y, and z axes. So you'd think that if carbon just used those orbitals to bond, a molecule like methane, CH4, should have 90-degree angles, but it doesn't. We know for a fact methane is a perfect tetrahedron with bond angles of 109.5 degrees. So why? The answer is this absolutely brilliant concept called hybridization. It turns out, to get the most stable arrangement and make the strongest bonds possible, atoms will often average out their orbitals. It's like they're mixing ingredients. For methane, the carbon atom takes its 1 s orbital and its 3 p orbitals, throws them into a mathematical blender, and out pop 4 brand new identical hybrid orbitals called sp3 orbitals. And what is the most stable way for 4 identical things to arrange themselves in 3D space, to get as far away from each other as possible? They point to the corners of a tetrahedron with angles of exactly 109.5 degrees. This is the amazing part. The theory doesn't just get close, it predicts the shape of methane perfectly, right from first principles. And it's not just a one-trick pony for methane. This idea explains so much. If you mix 1 s and 2 p orbitals, you get sp2 hybridization, which perfectly explains why molecules like ethylene are flat. 1 s and 1 p gives you sp hybridization, which explains why acetylene is a straight line. It even explains the incredible stability of ring molecules like benzene, or the electron waves are literally smeared across the entire molecule. So here's the bottom line, the crucial point. We've gone from a model that was just a simple drawing to a full-blown theory rooted in quantum physics that predicts the actual observable shapes and properties of molecules. It's not just describing what we see, it's predicting it before we even see it. And that just leaves you with this incredible thought. This model is so powerful, it can predict the shapes and properties of molecules that we haven't even made yet. It's the absolute foundation for designing new medicines, new materials, everything. And it makes you wonder, what other secrets of the universe are still hiding inside these beautiful, functional waves of probability?